Yes, the recording has started.
Oh, good.
So, yeah, hello everyone. Thank you for joining this webinar. And today we have with us Josh Armitage. He's going to talk about tribology and triboelectric effect. So, just to give a brief introduction about Josh, he has completed his PhD in this March from University of Leeds, and Josh has been working as a research impact fellow at the University of the Leeds as well under this ESPRC friction program grant, and his research encompasses the surface physical phenomena that are often overlooked, like primary electronic phenomena such as piezoelectric, flexoelectric, and triboelectric surface mechanisms on the macro scale. So today he'll be talking about his work during his PhD. So Josh, thank you so much for accepting our invitation and welcome for this seminar. So over to you.
Great stuff. Thank you very much, Manoj, and thanks for the invitation. Thanks to everybody for coming along to have a look at the talk. So thank you for the introduction. I'm Josh Armitage. I'm a PDRA, so job title's Research Impact Fellow, but I'm effectively a PDRA at the University of Leeds. My research in tribology is looking at the overlooked aspects of tribology. So when I first started my PhD project, I had a bit of a talk with my supervisor at the time was Professor Anne Neville, and she was, after a career of looking at surface degradation and minimizing friction, she wanted to think of a way where we can use friction and material wear for something useful, something positive, rather than just trying to mitigate it all the time. So with my physics background, the first thing that kind of jumped out to me was, well, when we rub things together, when we rub dissimilar materials together, we get a buildup of electrostatic charge, and that can be quite useful in some aspects. You know, there's something that I think there's something that we can work on there. So just to give a kind of quick background of the science that we kind of do, and give an overview of the triboelectric effect itself. I'm sure a lot of you have come across, let me just sort out, there we are, this lovely device here in your high school physics lessons. It's a Van de Graaff generator, and it's used to generate incredibly high voltages, where you have an incredibly high electric potential between the two orbs. And the way that's built is purely through the contact of a rubber sheet and several rollers. So people think it's the comb that scrapes along the sheets and you get a transference of charge, but actually it's the roller. But enough of the minutiae. Really what happens is we have a transference of electronic charge between these two materials purely through them being contacted together. And through the nature of that contact, we're able to generate incredibly high voltages that you see in this Van de Graaff generator. And of course, you can see this all over the place in daily life, and probably the biggest example we see of electrostatic discharge is lightning itself, and that's purely caused from the buildup and collision of dust and ice particles. So ice and liquid water as well. It's obviously same chemical structure, but a different orientation of atoms and molecules within the material. A different electronic structure, and when you have a contact between those differing electronic structures, you get a transference of charge, and of course that builds up over time, and it's got to be discharged somewhere, and that's where we get lightning bolts. So to give an overview of what I'm actually going to go over in this talk, I'm going to go over what the triboelectric effect is, how it's used in industry, how we can use it by how it's implicated in industry, and how we can use it for the better. And I'll go over the research that we'll be going over in Leeds into looking at the triboelectric effects and the tribology of it. So long story short, as we know, the triboelectric effect is the transference of electronic charge purely through the physical contact of materials. So what is transferred actually? What do we actually have being moved across this interface? Is it electrons or is it ions? So I'm going to go over a bit of a background of what the actual mechanisms of charge transfer is. So first off, electrons. We all know what electrons are mostly in terms of how they fit in the structure of materials. So when we look at materials as a whole, we know that electrons cannot occupy the same quantum states, so therefore they start at low energy states and build their way up. So when you look at a material, you have a whole spectra of electrons from lower energy states, the ground state, closely orbiting the nucleus of their atoms, to high energy states, which are normally, conductive, electrons that are used for conductance in metals and such. So an important term to just kind of go over now is a thing called the Fermi level. The Fermi level is the level at which the highest energy electrons are normally situated at zero temperature. So the easiest way to describe it is you have a bucket being filled up with water. The water is electrons and the bucket is the material. And the Fermi level is the surface of this water. As you're putting more electrons into the material, the energy, the water level goes higher and higher. And even to complicate things further, as you heat up the material, you get a change in this level. So you get, as you would get water molecules evaporating and moving out of the bucket, you get electrons going to higher energy states and evaporating out of the material through a thing called thermionic emission. That's just a kind of brief overview of how electrons behave within materials. How that correlates to actual triboelectric charging is, carrying on from here. Different materials, different surfaces have different chemical bonds, different ways that different atoms are being put together, how they're bonded, and different structures ranging from polymers to metals to ceramics, etc., etc. And the important thing to note is overall, in general, the stronger the bonds are between atoms and molecules, the lower the more energy you need to break these bonds. And that makes sense in terms of the energies within the electrons that are taking part in those bonds. It's harder for you to remove them. It's harder for you to break the bond. It's harder for you to remove the electrons from that material. So well-bonded materials, it's very difficult for you to take electrons from that material. Whereas if you have a very weakly bonded material, it's quite easy for you to remove electrons from it. And that difference in electronic structure is what causes triboelectric charge transfer. So the simplest thing we can think of is if we contact two metals together. And these metals are different. We have gold and aluminium. The two of them have different work functions. So even though they're both metallic, there is a difference in the amount of energy required to remove electrons from that material. And what we find is when we bring those two metals together, electrons transfer from one to the other. They transfer from the material where the electrons are in the highest energy states, so they require the least amount of energy to be kicked out of the material. So in this case, it's aluminium. It has a very low work function, therefore it's easy to remove electrons from it. And that you can see that in terms of its physical properties. Aluminium is incredibly reactive. It readily creates a passive oxide layer when exposed to air. So it's something where the electrons are very easy to be removed. They're very easy to react with things. Conversely, you have gold, whereas it has a relatively high work function. It's difficult to remove electrons from that material. Therefore, it doesn't really react with anything, and it's known as a noble metal. So when we put the two in contact, we have electrons being transferred across from the aluminium to the gold surface. And that there is an example of galvanic corrosion. So when you have the two metals in contact with each other, you normally see the aluminium corrode over time. So even though it readily creates a passive oxide layer, it does still corrode in situations here where it's you have this transference of electrons away from the aluminium surface. And this happens not just for metals, but it happens for insulating materials. And it's mostly noted in insulating materials as well, because once you have this transference of charge, because there are no available states for electrons to go into at the Fermi level, normally they are isolated in trap states, which means they cannot be conducted throughout the material and they stay on the surface. They're retained to that insulating surface. And the easiest way to see that in daily life is, if you wear a woolly jumper all day and you take the jumper off and it starts to attract the hairs on your body, the charge is retained on the insulating jumper surface. And you see that you can experience the electrostatic field generated by those trapped charges. And the strain of the material can affect this electronic structure as well. So as you start to stretch it, you're stretching bonds, you're putting energy into those bonds and making it easier for electrons to be removed from them. So therefore, you're changing the effective work function of them purely by deforming these materials. In addition to electron transfer, when you have liquids involved, if you have a droplet of liquid being dropped onto a solid surface, you have electron transfer between molecules in the liquid and atoms on the solid surface. And obviously, because you have that mobility of atoms within the liquid, you have these newly created ions that have either donated or gained electrons. They then move to screen this generated charge on the solid surface. So what you get there is a deposition of ions on the solid surface as the liquid drop is moved away. So hopefully the graph on the right hand, the figure that we have on the right hand side is giving a better visual representation of how that happens, where we have an electronic charge transfer happening and generating ions in the liquid, and therefore those ions are then moving to screen this electric field that's being generated. And once again, this is mostly how galvanic corrosion works when you involve a liquid. So how does this affect industry? In industry, a lot of people know that you have to ground fuel transfer systems because you have fuel moving it's moving across a surface, a surface that has a different electronic structure to the fuel itself. So you get a buildup of static charge within the fuel and on the walls of the fuel transport system itself. So it's really important to ground that system, or at least mitigate the amount of charges being generated, to avoid electronic discharge and a potential ignition of the fuel. Similarly, on aircraft fuselages, you can get a buildup of charge on the outside of the aircraft, and that can, once you have this buildup of charge, it essentially turns the plane into a lightning rod. It makes it energetically favourable for more electrons to travel towards it, making it more favourable to be hit by lightning, which is why we have electrostatic wicks on planes to help dissipate that charge back into the air. Carrying on as well, you get electrostatic charging between similar particles. So when you have powders, powder particles of different sizes, so the geometry of a system can affect the electronic structure. And as you have these particles interacting, both with themselves and with the walls of the powder handling system, you get electrostatic clumping, you get a buildup of charge and a potential for, if you have a flammable powder, you have the likelihood of the ignition of that powder if you're not too careful. So how can we actually use this for some benefit? We use triboelectric nanogenerators. The easiest way to describe the way that these things work is we have two surfaces that are put into contact. They have dissimilar materials to generate the most charge, and when you move those charges relative to each other, you then generate an external, you drive a current through an external circuit. So these can be used as motion sensors, velocity sensors, position sensors, and they can be used as a way to recycle otherwise wasted mechanical energy. The real downside of these particular devices is the fact that you are basing a generator on the fact that you are contacting materials. So naturally you have material wear. So now there's a push for people to develop materials that are able to maximize this charge while also limiting the lowering friction for efficiency of use, but also minimizing wear. So yeah, this has got applications all over the place in terms of motion sensors, energy recycling. I'm not going to go too much into detail of that, but I'll go over the operation of these things now. So they can come in a multitude of different orientations, and here are just a few kind of examples to kind of show how they work really. So what we have on top left here, we have the red block is an electrophilic insulating material. It loves to accept electrons, and once it contacts a surface, it retains those electrons on its own surface. And as that surface moves relative to a conductor, you have mirror charges that are moving within that conductor to compensate for the electric field that's being generated. So when you have a movement of these trapped charges, you're then able to generate this current through the external circuit. I hope I'm explaining that well to you lot. So what we then have is, I'll skip through this because really this is just an example of what we're doing here at Leeds. So I have replicated what we have as a triboelectric generator within a reciprocating tribometer. And its mode of operation is we have some insulating surface being brought into contact with either another insulating surface or a metal surface. We have a reciprocating contact where charge is being generated electrostatically within it, and the movement of those charges is then registered, it's measured by the external circuit. And the main way that we measure this is by having two electrodes, one at either end of the stroke, normally quite as large as we can with a very small separation distance, to force those mirror charges to move through the external circuit rather than directly conducting or discharging between them. So what we get from that is we get both, we're able to measure friction as well, of course, between the block, the two samples as we're sliding, and we're able to get a measurement of the current that's passing through the external circuit as well as the voltage. So we're measuring the electric potential between the two electrodes at any given time. So here's a general idea of how I put everything together. Long story short, we have two electrometers, one connected to each electrode, and a load resistance, which we can modify the resistive and capacitive properties of between the two of them, which allows us to measure current, it allows us to measure voltage, it allows us to measure a variety of different configurations of electronic properties, and allows us to change the circuit to have a look at options for power management, as well as directly looking at the output, the electronic output of this contact itself. So carrying on, the data that we get stereotypical friction data, as you're all aware. We get very nice, as you would expect for a reciprocating test, so I won't really go too much into detail with this. But we also get a nice reciprocating data from current. So as the block is being moved backwards and forwards, we are generating a current, an alternating current. As we have our forward and reverse stroke, we have a forward and reverse current. And we see as we change the resistance between the two electrodes, we're able to then modify the electronic properties that we're measuring. So this here, we just have a fairly low resistance. It's 10 mega ohms, but relative compared to an open circuit, that's incredibly low. And we find that the current that we measure is its ohmic response. So it's equal to what you would expect when you use Ohm's law from the voltage, essentially. So we have a resistance of 10 mega ohms. We expect 2 volts to be transferred into 200 nanoamps. When we increase that resistance, though, we start to see what things are like in the open circuit realm. So the voltage now directly corresponds to the position of the block over time, which makes sense because if you have an infinite resistance, the potential between the two electrodes will directly depend on where the block is, where the static charges are relative along the stroke relative to the position of the two electrodes. And the current we measure, it's just a matter of how quickly those charges are moving, so how quickly that electric potential is changing. So the faster the block moves, the higher the current we measure. So here's just a quick overview of some of the example outputs that we get. And one really important thing to notice is when we're looking at the current, even though that we have this what we expect to be a fairly uniform charge distribution moving backwards and forwards in a sinusoidal fashion, because that's our velocity profile of the block, we're not getting a perfect sine wave for current and voltage. So I've done some finite element analysis, some electrostatic modeling to find out why exactly that happens. So looking at it here, on the left-hand side on the image here, we have what we can expect to be a completely uniform charge distribution along the bottom of this red block here. So that means we have a constant charge distribution. There's no peaks or troughs, that it's a constant charge density across the whole surface. And the black line here is what we would expect to see from that charge distribution. What we do see is the blue line, and the model that we've managed to replicate that's giving this output. It's showing that the block, when we bring it into contact, is actually edge loaded, and it's in some circumstances it is asymmetrically edge loaded. So you can see here where one edge of a block, possibly like this side here, has got a higher density of charge than the other edge of the block, and in the middle we're not actually getting as much contact or as much contact pressure that we would expect. Which makes sense when you have plate-on-plate contacts. You normally tend to see the edges of the edges of that contact having a higher contact pressure due to the edge loading effect, essentially. So carrying on from that, we've also spotted some really interesting data, as well as seeing our overarching alternating current between the two electrodes as we move the block. We're also seeing very small, very quick spikes in current, which we're actually attributing at the moment to electrostatic discharges happening across the contact. So we had the buildup of charge, but then what I can describe as very tiny microscale lightning bolts happening across the contact. So we get a buildup of charge, and when that charge is when there's so much charge within an area, we reach a saturation level. If we put more charge on there, within that area, it becomes energetically favourable for that charge to then tunnel back. And normally that leads to electrostatic discharge happening. And that's what we're attributing these events to. So in terms of how I can physically measure the charge on the bottom of the red block within the contact at any given time on our test, with it being a reciprocating test, I'm able to get this alternating current data. So for example, this graph here is showing a forward stroke and a reverse stroke for our block moving backwards and forwards. What I tend to do is I integrate the current. There we are. So integrate the current with respect to time and you get a value for charge. We do this for every forward and every reverse stroke, and then it allows us to plot the charge on the bottom of a block with respect to time, with respect to sliding distance across the duration of every test. We also do this for these tiny events. So what we do is we integrate under every individual, we call it an ESD event, every abrupt movement of charge, and then we separate that from the underlying data. And what we get there is a value of charge that is electrostatically discharged for every stroke. And when I plot the total contact charge in blue, which is the charge on the bottom within the contact for any given stroke, and the red is the charge that is discharged across that stroke. And we see the higher the charge density we have within the contact, the more likely it is to be discharged. So it's giving us an idea of a competing mechanism where the blue is the buildup of charge over time and the red is the dissipation of charge. So we have two competing mechanisms there. Also, I'm able to obviously compare this contact charge with friction data, with the amount of energy we're putting into the contact via friction, and ultimately we're able to measure the energy, the energy being input to the contact via friction, and comparing that to the output energy that we see being given off by the device itself. So we're comparing that over time, and for a lot of our tests, we're finding that friction is correlating very well to the charge that's accumulating within the contact. Now, there are multiple mechanisms that are all playing into this. So I can, at the moment, I cannot attribute it to any one mechanism. But when, which I'll be going into more detail in future in the following slides. When we don't have contact, so for example, if I build up a charge within our contact, I then separate the surfaces by a certain amount. So for example, in this test, I separate the surfaces by 1 millimeter. I then begin to reciprocate the block in non-contact mode. We're not going to get any friction data, but we still do get a measurement of charge. And more importantly, we're able to see how that charge changes over time on the surface when it's exposed to air. And what we found is the charge on the insulating surface decays over time, which we expect to see when we're thinking about thermionic emission. So as we expose a charged surface to air, we have air molecules coming onto the surface, reacting, exchanging electrons, and ultimately dissipating that electrostatic charge. And we found that it is almost perfectly exponential in nature. Also, we've been modelling the accumulation of charge within our contacts. Clearly, there are a lot of different mechanisms that are all playing together and all competing and changing the way that the charge is being built up within a contact. But most of the time we're able to fit a dual exponential to these plots, one to approximate the normal accumulation of charge as you would in a capacitor. Essentially, you build up charge up to a saturation level and you can't go beyond that. And the second exponential is normally there to describe either the formation of transfer layers, so we have a buildup of material within the contact that is inhibiting charge transfer. Also, it can be used to model the truncation of the actual texture of the contact itself. So as you wear away the surface and you remove particles from it, you get a larger contact area because the textures are being truncated and they become more conformal, and you get a larger surface area within the contact over time. We've also compared different materials, so we've compared different plastics in contact with metals, and we've effectively put together an effective triboelectric series, as previous studies have done, ranking materials in terms of how well they donate or accept electrons in response to contact with different materials. So we found that agreeing with previous studies, Teflon, PTFE, polytetrafluoroethylene, is incredibly electrophilic. It loves to accept electrons, and that's due to its molecular structure. Happy to go into detail with that if anybody requests towards the end. And conversely, we have nylon and Delrin, so acetal, polyoxymethylene, and I cannot remember the name entirely, but nylon, they are incredibly electrophobic in terms of they love to donate their electrons to other surfaces, and that is once again specifically due to the interpolymer chain hydrogen bonds, meaning you have electrons in very high energy states that like to be donated to other materials. And carrying on, we've investigated the texture of the contacts and how that correlates to charge. We have found that the more conformal surfaces are, the more likely we are to get more charge within that contact. So it's directly correlating to the real area of contact within that sliding block on plate motion, as well as we look into the applied load and the sliding speed. So looking into the applied load, as we increase it, as I'm sure many of you are aware, you increase the applied load to a contact, you're increasing the real contact area within that, especially at low loads. So this is quite a low load, very low contact pressure, with it being a plate-on-plate contact. So most of this increase of load it's not going into increasing the contact pressure, it's going to increase the real area of contact. So we see that as we increase the load, we're increasing the amount of sites available for charge transfer by increasing the real area of contact. And you can see here the black, the blue, the green, and the red, all different contact forces, alluding to different amounts of charge that's being generated within the contact. And once this as well, when we're looking at the sliding speed, we're seeing a very clear difference in the buildup of charge when we're changing the sliding speed of this reciprocating contact. The important thing to note here is that the increase in contact charge by increasing the sliding speed is not due to just introducing new sites. So the best way to describe it, like Volta initially proposed that the only reason why sliding friction increases the charge of a contact is because you're introducing new areas on the surface that can then donate charge. But since it's a reciprocating contact, you're giving a very limited amount of time for charge to be replenished on the lower surface. And from calculating the charge decay times when you expose those surfaces to air, it's actually very negligible that when you have the block move out of contact, the interactions with the air does not replenish the charge on that lower surface. So the hypothesis is that it's something to do with the nature of the contact itself that's actually expediting the charge transfer. And right now we're attributing that to the production of phonons, so quantized vibrations, which we're all aware of frictional heating. We're all aware of acoustic vibrations within sliding contacts, and that's essentially one of the one of the phenomena that is shown by phonons. They are quantized vibrations. They can be, they can express themselves as heat. They can express themselves as sound. And when you see that in a sliding contact, they are able to interact with electrons, with surface electrons, give them more energy and make them more likely to be transferred from one material to another. So that's our current hypothesis for how sliding contact expedites the generation of charge within these sliding contacts. And also, as I mentioned earlier, we're looking at things like material wear. We're looking at the transfer layers being generated, specifically with, I'm sure many people will know how PTFE, how Teflon acts in dry lubrication. It's a very low friction material purely because it likes to, it has a low surface energy, but also it favorably wears and generates a low friction Teflon counter surface transfer layer on the harder counter surface that it's rubbing against. So that lowers friction over time, but it also lowers the amount of sites that we have for charge transfer. So as we see friction lowering over time, with the green line here in the middle graph, we also see a decrease in contact charge over time as well. So that's how this kind of synergistic relationship happens with Teflon contact. We're also able to observe things like the removal of significant wear debris. So we see here for this nylon contact against aluminium, we have clearly some fluctuation in friction coefficient and a reduction in contact charge, meaning that we have charged wear debris being removed from the contact, and that's being observed in situ. In addition to that, we've had a look at how lubrication may affect charge transfer. We're not looking, unfortunately, at things like oil lubricants or anything that's actually very useful for engineering purposes. My initial tests have been looking at something that we can put into a contact but then quickly remove. So what I have done is I have introduced a small drop of heptane into this plate-on-plate contact. We see a drastic drop in charge as the electrons are being donated to the heptane rather than any solid surface. So we have a lowering of friction and we have a lowering of contact charge over time. But as that heptane evaporates away and it's being starved from the contact, we then do see an increase in friction over time, but we also see that charge being built up again over time. And another thing to notice is when I go to measure the electrostatic discharge events for these contacts, we see that when lubricated, we have no events. And once that lubricant then starts to dry away, we start to get more of those discharge events happening. But yeah, in conclusion, we've managed to replicate a triboelectric generator, a reciprocating contact within a tribometer environment. We're able to look at contact force, we're able to look at sliding speed, we're able to investigate different material compositions and textures. And right now we're looking into what the actual mechanisms are for this charge transfer and how tribology is affecting the build-up of electrostatic charge within a contact. So hopefully I was able to explain everything reasonably well for everyone. Hopefully I gave a good overview of our work here at Leeds. If you have any questions, I'm more than happy to answer any, and feel free to send me an email if you have any further inquiries. Thanks again for listening, everyone.
Thanks to you, Josh. It was outstanding. Very easy to follow, even for people that have never heard of anything like this. We had a few questions on chat, so well, you're able to read them, but I would say just to go in order. The first one is from Jen Ballard. What is the advantage over piezo technology?
So yeah,
you get that a lot.
Yeah, so I mean, piezo technology has its advantages in terms of it can be used it's used for different applications. It's purely from the introduction of strain over crystalline materials or materials that have that asymmetry in charge in their molecular structure. The thing with piezo technology is the retainment of charge on the surfaces. So, for example, with triboelectric, you have the contacting of insulating surfaces. You have that entrapment of charges. You have the entrapment of electrons in For example, in PTFE, they become donated to the carbon backbone in PTFE because that's where a lot of low energy unoccupied electron states are. So those electrons are retained quite well within the Teflon. Teflon is actually, it's a material that really loves to hold on to its charge over time, and it makes it quite difficult for me to test with in terms of removing that charge before I start a test. But in terms of piezo technology, that charge, the moment you remove the strain, the charge is then, it's no longer there because you don't have that disparity in electron cloud throughout the material. Hopefully that explains a little bit better, but piezo technology can be used in conjunction with triboelectric technology as well. There's no reason for there to be competing. They can be used in addition to each other.
Sure.
Cool, thank you.
I've kind of unmuted Lilian. Maybe he could ask his question.
Okay.
Yeah.
Yeah, thank you, Josh, for an excellent talk. Can you hear me okay?
Yep, can hear you well.
Yeah, I was thinking about your discussion of the sliding mode, and you said that it basically stretches the strain, stretches the bonds, right?
Yeah, so we have two kind of main ways in which this happens. We have the deformation of the material in any kind of way, whether we're deforming it through application of normal load or through a tangential load through sliding. But in addition to that, we do also have these vibrations that are being introduced by sliding contact. The main thing. Oh, yeah, sorry.
I understand. So then, if you had something like really adhesive, for example, say PDMS as opposed to Teflon, and you, instead of using a sliding mode, which is what you've shown in your data, you use what an AFM does, which is a compression and then release. That also stretches the bonds, but then I think if it's an adhesive contact, then I would assume that the bonds get stretched more, and that would be there would be a difference in the ability to release or charge. Could you comment a little bit on that?
Yeah, exactly. So this is actually something I'm hoping to move my research forward to investigate it on a nanoscale with AFM. I think that adhesion is definitely, not only does it play a part mechanically in terms of the stretching of bonds upon release, and it will, I think the main way that enhances it, but I believe it would enhance charge transfer, is because not only are you then modifying the electronic structure by compressing it in one way, but as you're bonds that may be stretched one way may be compressed the other way, and vice versa. You're diversifying the electron states within that surface. You're diversifying both the spectra of electrons that are in states of the donor surface. So you have more electrons in high energy states, but conversely you have more unoccupied energy states within the other material that might be lowering in energy by stretching or compressing bonds perhaps. So that's in a nutshell the best way to describe that is through the flexoelectric effect, and that's purely through having a strain gradient in a material induces a change in surface potential purely from this modification of the physical structure leading to a change of the electronic structure, if that makes sense.
Yes, thank you for answering.
No, thank you very much for your question.
There's a second question from the same person. Will you share the slides with everyone, Josh?
Sharing the slides?
Yeah, your slides.
Yes, of course.
People would
Yeah,
love to.
I'll send Manoj the slide deck so that can then be distributed to everybody.
Super, thanks a lot.
Yes, and also we will have this recording on our website, so I think it would be good.
Next question comes from Jan Pilart. I hope I'm doing it, saying it right. Could you unmute him, Manoj? I think it's more didactic.
Yes, I think I've given the access. He can unmute himself and ask the question.
Yes, I was just asking because you mentioned that the contact area has more impact on the transfer of charges than the contact pressure, and I wanted to know if you did some experiments to prove this.
Yeah, so in terms of our macro scale test, it's purely looking at the increase of the real area of contact. So the way we've the way we've determined that the increasing load is mainly contributing to an increase in contact area rather than an increase in pressure is purely from we have a static contact model that essentially we plug the materials into, we plug the tribological properties into. We have interferometry texture scans of the two surfaces. We model them both being brought into contact, and essentially from that we get an idea of what the real area of contact is between those. The real area of contact, as well as the contact pressure and the distribution of that pressure, is between those two surfaces. But moving back to your actual question, how the increase in contact area opposed to the actual contact pressure within that area itself, I believe that not only does the real area of contact affect the buildup of charge, I think the pressure within that area of contact also works to enhance the charge, the charge generation within the real area of contact. Purely because if you have an area which is being contacted, if you have a higher contact pressure within that area, that same area, you're more likely to have the atoms, the surface atoms that are contacting within that area are under higher deformation. Therefore, their electronic structure would be more diverse. Bonds within the surface will be more deformed. There'll be more. Electronic structure will be modified further from what the surface would have been at under no load. So when we bring the surface into contact, obviously we start with a surface as being completely undeformed. We'll get charge transfer with that particular electronic structure. But as we begin to indent, we're gradually changing the electronic structure by changing the amount of deformation in the surface. And all throughout this time, as we're deforming the surface, we're changing the electronic structure, and therefore allowing electrons to move between different energy states which may have not been available under different levels of deformation. Does that hopefully that explains reasonably well my thoughts on it?
Yes, it does indeed. Thank you.
Thank you.
I just had a short question when you showed this picture with the dissipating and charging effects. I was wondering about the displaying of the graph. Like, was the red one the noise more or less, like charging and discharging projects? Or I had to sneeze, so I couldn't follow properly what you said.
That's all right. It's also me as well, because I've been trying to cram in a fair bit to a short amount of time, to be fair. So it's good to have the opportunity for me to explain this in a little bit more detail. So when you look at this graph itself, the blue area is our background output. It's purely the charge the current that we generate purely from the physical movement of the block from one electrode to the other being slid across. Whereas the red spikes are caused by charge being moved across the contact. So from the red block to, in the diagram, it's the blue sheet. So it's being transferred directly across the contact in a very short amount of time. So what I've done is separate the two amounts of charge. So the blue is let's say that the blue is the total amount of charge that we have on the surface during the sliding motion. The red is what I can only say to be the change in charge. It's how much charge we accumulate or dissipate by these very, very quick, very abrupt events. I'm hoping I'm explaining that reasonably well, but
yeah.
because we're also trying to determine the nature of these events as well. My current understanding and what I kind of believe them to be at the moment is this movement of we've measured the charge value for each one. It's roughly like a few thousand electrons being moved at a given time. So it's striking me as, rather than it being like the movement of an ion, like as in a very small bit of wear debris or something moving across the contact, it's looking to me more like an actual electronic phenomena.
Okay, thank you very much.
Thank you for your question.
I think the next question is from Nisha Singh.
Yeah, I think she can unmute.
She can unmute? Okay, thank you, Anish. Otherwise, we will read her question.
I've just had a read in the chat. So it's, is there any effect of frictional electrification on the tribological behavior? So where my research is looking at the influence of tribology on charging, the question is whether there's the reverse as well. So what we do see when we have these charged surfaces being contacted, we do have positive and negative charges being in very close proximity. So you would expect there to be what I would call a Coulomb adhesion between the surfaces, because we have these positive and negative charges in very close proximity. Unfortunately, I'm currently modifying our contact model to calculate the magnitude of this adhesion for our surfaces, but I believe there actually has been a paper that's been investigating whether the amount of charge within a contact actually enhances friction. And so far, I think the general consensus is the more charge you have, the greater this Coulomb adhesion, therefore the higher the frictional resistance we get in the sliding contacts.
Nice. And then the last one is a short question. Energy density, is it watt square millimeter or watt by cubic millimeter?
Okay, so the energy density, I believe I'm not sure whether I actually mentioned the energy density of these devices as a whole throughout. So obviously the energy density can be expressed in either of those units, but that shows you the dimensions in which that energy is being stored, if that makes sense. So, you know, for example, if you have it can be expressed in terms of charge as well. So you have a surface and you have a surface charge density, that'll be in coulombs per millimeter squared. Whereas if you have a volumetric charge density, you have coulombs per millimeters cubed. All of our charge densities are surface charge densities because we don't expect much charge injection further into the bulk of the material. So that's always going to be coulombs per millimeter squared. But in terms of the devices themselves, the real important thing here for kind of enhancing the output of them and making them more applicable for industry applications is the fact that even though it's quite a large surface area that we're building charge on and not getting as much electric output as we'd like from that surface area, we can make these devices incredibly thin and incredibly flexible, and they're incredibly adaptable in terms of geometry and how they can fit into different systems, which makes them stackable. And when you start to compare the volumetric energy density to the a surface energy density, you find that the volumetric energy density of these devices can actually be amplified quite a bit, especially in comparison to like conventional electromagnetic generators, which, due to the mode of operation, they're quite bulky, they require very high relative speeds in order to induce that electric current through the electromagnetic induction rather than our electrostatic induction. So ultimately, it's quite a high volumetric energy density that we're getting. I'm afraid I can't quote any exact values, but there's a lot of data out there, a lot of papers out there, which hopefully will be able to give you an answer.
Thank you, Josh. That was great, actually. I think we are done with the questions in the chat. If I missed any, please let me know or scream. That's good. Cool. As well, Josh had his email on his last slide, so I guess that means that he is open to one-to-one communication.
Yeah, feel free to and enjoy more of a GIF if you'd like.
Love it. Cool. So lastly, I'll give the word back to Manoj, please.
Yes, thank you, Savi. Thank you, Josh, for this wonderful talk. I know that this field is a very niche field in tribology, like where still the research is going on, and you have done really very well in understanding of this tribo nanoelectric generators. So I really thank you for your time and your presentation, and also for accepting our invitation. And also I thank everyone for attending this seminar. And we will be back with our next seminar soon. So until then, see you and thank you. We'll end this.
Thank you, everybody.
Have a good holidays. Ciao.
Yeah.
Bye.
Bye.